versus integral. So integral calculus, the idea is that a function has what we call an integral function. And that integral function finds the area. It's one way to look at it. Between the function curve and the x-axis. And a super simple example that I'll relate back to the differential calculus idea is, let's take similar idea to what I had yesterday. Let's take the simple function f of x equals 60. And this is going to be my velocity function. So I'm on the highway and I set my cruise control to 60 miles per hour. Okay. So this axis right here is velocity axis. This axis here is time. Velocity, let's say that's miles per hour. And the time axis is going to be measured in hours. And 1, 2, 3 hours could go by. I can turn velocity into total distance, accumulated distance, because I have this idea that distance equals rate times time. What's my rate? Well, it's f of x, it's 60. My rate is fixed. So this one's pretty straightforward. So if I went 2 hours, then I would simply take my 60 miles per hour, multiply by my 2 hours. Hours divide out there, and I simply get 60 miles, 120, I can multiply, in terms of accumulated distance. Pretty straightforward. Now, the cool thing about that is when I made that calculation, graphically, I'm taking this height of 60 here on the graph, and I'm taking this base width of 2, and I'm multiplying, and really that area right there is that 120. Okay, so the idea of taking speed, which is the rate of change, the derivative of position, and doing this idea of area under the curve between it and the x-axis, that's the idea of the integral. Now, sometimes that's really easy, like that was super easy. Okay. Now, what's my integral as a function? Okay, so the integral function, if I use lowercase f for the actual function, the integral function would be a capital F. Or we just give it some new name. Sometimes they call it A for area or accumulation. So sometimes we call it A of x. Sometimes we might call it capital F of x. We might call it capital F of x or A of x. It's simply my function, 60, times the x value that I've gone from 0 to. So in this case, it's just 60x. Right? That's my height times my base. All right, let's look at a slightly harder problem. Suppose, new page, my function was, go slightly harder, slightly easier, f of x equals 2x. What's that graph look like? Straight line, slope 2, pretty straightforward. Let's make a picture of that. 1, 2, 3, 4, 1, 2. And so we have the point 0, 0, we have the point 2, 4. And so there's my best sketch of that at the moment. And if I want to think about integral function here, let's just pick some random x value. I'm going to say that's my x value. The integral function would find the area from x equals 0 between the curve and the x-axis up to whatever x value I say stop at. Well, what shape did I just draw there? It's a triangle. I know the area of a triangle. Area is 1/2 base times height. Okay, so this is the vertex of the triangle. So whatever that is right there, that's the height. Well, how do I find the height? Well, doesn't the function give me the height right there? Yeah, so my base is whatever x is, and I'm just saying it's x. So I get 1/2, base is x. The height here is just 2x. Clean that up, I just get x squared. is my area function. No problem. Okay, so wow, that was a little easier than the last step I did with derivatives. But wait, let's throw a parabola in there and see what happens. All right, so how about f of x equals, let's do the same one we had, 4 minus x squared from before. We know what that graph looks like. 2, 3, 4, 2. It's got that vertex up there, and it drops down, concave down through that point right there. And if I just say pick some random x value, that one right there, somewhere between 1 and 2, I would like to find this area between x equals 0, x equals x, above the x-axis, but below this curve. Now, I know formulas for areas of triangles, and I know formulas for areas of rectangles, and I know formulas for areas of circles, but I don't remember before calculus learning a formula for the area under a curve like a parabola. Right? That's not covered in standard geometry. So what do? Well, at first, our only choice is to approximate that area. One way I might approximate that is I might just say, hey, well, let's just take this point right there and this point right there and connect the dots. What shape have I made when I connect the dots and I put a diagonal up there instead of a curve? Anybody know what that shape's called? Look at it sideways. Got a pair of parallel sides. It's a trapezoid. Parallelogram would have 2 pairs of parallel sides. A trapezoid has just 1 pair of opposite, well, parallel sides are opposite, but 1 pair of parallel sides. Yeah, that's a trapezoid right there. And there's a formula for an area of a trapezoid. It's going to be a little less than the area I want, but it's going to be close. Okay, someone says, I need you to get a little closer. Okay, so the standard technique for approximating these areas with curves at the top is just to break it up in a bunch of rectangular strips. Okay, so I'm just going to draw that a little bit bigger over here. So we're going to blow this up over here. So here's, oops, use the straight line tool maybe. Sometimes I don't do such a good job with straight lines. All right. So let's say this is a blown up version of that. Curves down there, through like that. So that's not a straight line, that's a curve. What we do is we break up the x-axis into a bunch of different segments. So I might break this into, let's say, 4 segments. And then from those segments, I just go straight up and straight up and straight up. And make believe those are all equal widths. Do they have to be? No, but I was hoping they'd be equal widths. I guess I can move them. This one just needs to move over a little bit. No. Can do this. Come on. Oh, please, just move. All right, doesn't want to move today. Make believe they're all the same width. Now, I still have a problem in that the tops of these are curved at the top. I could do the same thing I did before and use triangles, but the easier thing to do there is to just make them rectangles. To make this a rectangle, I either take the left-hand point and draw it across, or I take the right-hand point and draw it across. Take your pick. So if I do what's called a left end point approximation, I take each left end point and I turn these into actual rectangles, like that. In this case, if I did left-hand endpoints, I would get an over approximation. So what's the area of this rectangle right here? Well, it's whatever this y value is times whatever that distance is. And that's the area of that rectangle right there. And I just keep repeating that over and over again. We could do right-hand endpoints. If I did right-hand endpoints, I would just grab this side and go across, and this side and go across, and this side and go across, and that side and go across. And then I would get an underestimate of the area here. Now, these are upper estimates and lower estimates only because this is curving downward. If it were curving the other way, that would flip, if that makes any sense. And the actual area would be somewhere in between those two. How do I get a better approximation? Well, if somebody wanted a better approximation than that, what I would do is simply make skinnier rectangles. So I would just throw in more rectangles, maybe cut all these in half. And if they wanted a better approximation than that, guess what I would do again? Make the rectangles thinner and thinner and thinner and use more of them. And eventually it's going to exceed my calculator's ability to get any closer to the actual area. That's integral calculus. Sometimes, like remember we turned that slope into an actual 2? Sometimes there are tricks to actually find an exact value. And we can say this is definitely 2, or this is definitely pi over 4. But other times, all we can do is keep using skinnier and skinnier rectangles. Some of these problems are unsolvable except with a computer. That's life. Not everything has a solution that is like, solving 2x plus 1 equals 3. That's integral calculus. Again, the relationship between these two, derivative calculus turns like position into speed. Integral calculus turns speed into position. They reverse each other like multiplication and division. Derivative is a kind of division, and integral is a special kind of multiplication. And we're going to spend all of this quarter learning derivatives and all of next quarter learning integrals and how they're related. Questions?